Let's finish up the benzylic chemistry handout. We synthesized that, right, in class? That's where we ended up at?
Yes.
We're ready to start now the Diazonium chemistry. Next page. Any questions about benzylic oxidation or benzylic halogenation, bromination? Okay, Diazonium chemistry, sometimes called Sandmeyer reaction. Sandmeyer, one of the original chemists, developed this chemistry. More generally, I think called Diazonium chemistry because the intermediate we're going to form is a diazonium. Two nitrogens, di, Azo nitrogen, it's an ion. This is the reaction of your anilines. Either just plain aniline or substituted anilines. You meet them on the benzene ring. Very versatile reaction. We can make the diazonium by reaction with nitrite and a proton source. That's what that is. Be potassium nitrite, sodium nitrite, etc. Sodium nitrite, not nitrate, nitrite, NO2, proton source. NO2 minus. If we protonate NO2 minus with a proton source, what would that give? HNO2. You can draw it out. What do we call that? Not nitric acid, but nitrous acid. HNO2. Nitrous acid is what. The problem is nitrous acid is not a stable acid. You cannot go to the stock room and say, give me some nitrous acid. You cannot order nitrous acid from a chemical supplier. It's not stable. But you can order the nitrite anion. And you create nitrous acid in situ, in the reaction, by just supplying a proton source. Another way to write HNO2 is that. That's HNO2 also. But if you write it like that, then you can say HONO. Okay? So this is HNO2. Now, of course, if you do a Lewis structure, you get something like that. Indeed, it is HONO. Okay? That's just fully condensed. Nitrous acid is what we react our anilines with. Okay? To form the diazonium. Obviously, another nitrogen is on the first nitrogen. Mechanism for forming the diazonium. Let's wait a little bit. We'll talk about that. But once you make the diazonium, we can then replace the two nitrogens with a variety of things, a variety of groups. We can do substitution. Let's skip the F first. Let's start here. We can replace the diazonium with a chlorine, that's just the benzene ring, chlorine or bromine, using copper chloride or copper bromide. Why copper? First off, sodium chloride and sodium bromide does not work. You have to have the copper or probably some other transition metal. Most of these reactions to replace the two nitrogens, it's a radical reaction. Okay, not a SN2, obviously, because we're on an sp2 carbon. Usually not an SN1, it's usually radical. The copper helps it become a radical reaction. We're not going to look at most of these mechanisms. And usually when you use the copper, that's what Sandmeyer was known for. Now you can replace now when we replace the two nitrogens with something, what do we produce with the two nitrogens?
Nitrogen gas.
Yes, we produce nitrogen gas. When you did your diazonium last week, it asked you to look for the bubbling. That was the nitrogen gas being produced and bubbling out of your reaction. By the way, you used sodium nitrite last week, right? What acid did you use? You didn't use HCl. Paratoluene sulfonic acid. It's a dry acid. Okay, variety of proton sources. You can replace the nitrogen with iodide. With iodide, you don't need copper, because iodide can do redox by itself. And you can just use Ki, and that's what y'all used in lab, right? You didn't use copper iodide. We can go back to the F now. The F, you don't typically use just copper fluoride or something. Instead, you can see there, you treat your diazonium with HBF4. That's tetrafluoroboric acid. This leads to anion exchange, and the chlorine gets replaced with the BF4 minus. And this will usually precipitate. Where the diazonium, you never usually isolate this. The diazonium is just made in solution, and once you make it in solution, you then add in your other reagents. But if you exchange the anion, that will precipitate, and you usually will filter that off and actually isolate the diazonium tetrafluoroborate. Now we need to talk about isolation of diazoniums. Usually that's a no-no. Diazoniums are known to be a little explosive because they will separate into something in nitrogen gas, and that's very driven by entropy and thermodynamics. Usually you don't want to isolate a solid diazonium. Here you do. This is the best method. Of course, this method's about 50 years old now. Then you would take this and you would just heat the bejeebies out of that solid, and it would give you your product with an F there. You would also make nitrogen gas, and you would also get what if we just, like BF3. After heating your solid. Basically, you heat it and it would explode. But you would get your product out of it. A little bit dangerous. These tend to not be explosive, but there's a lot of more diazoniums that are not shown up here. For example, one of the scariest I've ever been in lab is when I was doing a diazonium reaction in graduate school, and we were trying to replace the nitrogen with sulfur. We wanted an SH on the ring. We made the diazonium. We were doing a large scale, and the flask was like the size of a basketball almost, volleyball, basketball size. And we prepared the diazonium by dripping in the solutions here into the amine, made the diazonium, everything was fine. Then we started dripping in the reagent to replace the nitrogen with the sulfur. It's called a xanthate. And as soon as that started dripping in, after about 10, 20, 30 seconds, maybe a minute, all of a sudden it went BAM! You ever heard like a go-kart or old Volkswagen backfire? Sounded like that. Okay? I was doing it with like a first-year graduate student. I was like probably third or fourth year. And so as soon as that happened, I took off running because I didn't. I told him to close the hood and stop that. We were doing it together. As I got around the corner, I heard it go bam again. So we didn't add any more. We added a lot of water and diluted it out, and just pretty much quenched it out by adding water and neutralizing it. But it was loud. This flask again was okay. So what? You know, about a year or two later, I read that diazonium sulfides are particularly explosive. I said, yeah, I believe. I should have read that before. I also should have been doing it on a huge scale. So, got to be careful about isolating diazoniums, especially if they're sort of unique. Now, one thing is tosylate diazoniums, such as made with using paratoluene sulfonic acid, are known to be particularly stable. One reason I like using them in the lab. If you're interested in that, all you got to do is Google. You know Google? Write in diazonium tosylate stability, and I'm sure you'll get a hit on it. Check it out. Okay. Let's see. If you just take your diazonium and heat it in water, you can replace the nitrogen with an OH. And what are you making here? What do you call this type of compound? Phenol. That's a great way to make phenols. And if you remember, we don't have a direct way to make phenols. We don't have, this is a great way to make the fluorine on the ring. As long as you don't have trouble with your diazonium. But you remember, putting fluorine directly on the ring using F2 is kind of pretty dangerous. That's more dangerous than that. Great way to make phenols. Okay? Now this may be where this just ionizes and you make cation here, and then water attacks cation. Maybe. And that would imply it's like an SN1. Most of the other is radical reactions. Let's skip this one. You can replace this with a cyano group, nitrile. By reaction with copper cyanide. Cuprous cyanide. Okay? And so we can get a cyano group with nitrile on the ring. That's similar to these up here with the copper. Okay, how about this guy? You can replace the diazonium with what? An H. Why would you want to do that? Basically, what are we converting aniline to when we do this and replace that with an H? Benzene. First off, nobody's making benzene this way. Because how do you make this? So you start with benzene, you nitrate it, you reduce it to the amine, and then you remove the amine. You're in like a big old circle loop here. Okay? So you wouldn't make benzene. But there are some specialized cases where you would want to do that. First off, what are we reacting with? H3PO2. What is that called? What is H3PO4? Phosphoric acid. What is HP3PO3? Phosphorus acid. What is H3PO2? No, it's not a new character on Star Wars. What is it? Hypophosphorus acid. Yes. That's it. Nobody calls it that. It's typically called phosphenic acid. Sort of a slang name. The main thing about phosphenic acid, it's a reducing acid. It will reduce things. Of course, when you replace something with an H, that's a reduction, right? Okay. It will supply reducing hydrogen. Phosphenic acid. There are other ways to do that. You can just just add in copper metal and just like ethanol, and you can do that reaction. Copper metal and a proton source. But phosphoric acid is the textbook way. We'll see when you might want to take advantage of that reaction to remove an amine, maybe a little bit later. So this is diazonium chemistry. Very versatile. One of these, they're just a little experimental if you want to read here. Mechanism for the diazonium. I do want to make a comment. You do not need to know any mechanism for the final products. You can mainly predict the product and we'll be using it in multi-step synthesis. Here. These create HONO. There's not an oxygen there. It's like this. That's HONO, right? You do need another H+. I'm going to kind of do it abbreviated here. You protonate this. Hold on, let me show you this. The reacting electrophile here from the HONO is 2468, 246. Is that right? 246. I reckon that's good. Look, good low structure, 8, positive charge. Yeah. Question, what's the electrophile that is the reacting species when you nitrate a ring? If you remember, it was this here, which is called what? Nitronium ion. This is when you nitrate the ring. You've got to make the nitronium ion. It's made from what? Nitric acid. Loss of water from nitric acid leads to the nitronium ion. Loss of water from nitrous acid leads to the nitroso ion. How do you lose water from this? First thing you do is protonate it. So you do have to have another H+. Now, anytime you can make a pi bond, you kick off the leaving group, that's easy to do. And that arrow movement gives your nitroso ion. Now the aniline, the amine, reacts with the nitroso ion. This nitrogen becomes bonded to another nitrogen, and the other nitrogen loses oxygen. I want you to do this mechanism on your own, and we'll look at it on Wednesday. How the aniline reacts with the nitroso ion. Keep in mind, we're under acidic conditions, so you have a proton source. It's nothing but standard electron movement to get where you need. Please give that a try. Okay. Instead of replacing the nitrogen with something by substitution reaction, essentially, we can also do what's known as a coupling reaction. Take an aniline reacting with HONO, make the diazonium. In this example, if we did throw in phenol, we can do an EAS reaction with phenol. That's sort of, take punched out. That's just the ring up there, yeah, and that's an OH. And what bond have we made? Right there. The ring is now bonded to the N nitrogen. What type of director is OH? Orthopara. We're reacting the ring here, so we're doing ring chemistry. It is EAS. Orthopara director. I'm showing para product. We may also get ortho. Basically, the bond is there. These electrons contact this nitrogen, and these can move over here to give that nitrogen what it wants. What does it want? It's already got a positive charge. Well, it's a lone pair and no positive charge. So attacking here, what does that give? Lone pair there now, double bond in between. Now what's bonded to this nitrogen? The ring. I'm doing a pair attack, leaving carbocation there. We can do resonance structures as always, including resonance using the OH, which is why it's an ortho-pair director. I'm not going to do resonance. There's an H here. Something then takes the H. What do you want to use to take the H?
X minus.
You can use X minus. It can be chlorine minus or sulfate minus. If it was a Cl minus, we would, or you could use water. And there you go. You get final product plus like HCl. So you're really doing an EAS reaction here, and this is your electrophile. You attack the terminal nitrogen. And so typically you use an activated aromatic to attack your diazonium. And phenol would be an activated aromatic in terms of activated for EAS. So usually you have activating groups on your ring that attacks the diazonium. It's called a coupling reaction, a diazo coupling. Two larger fragments coupling together. These things typically are dyes, called a diazo dye. Diazo, why is it a dye? It means it's highly colored. What makes this highly colored? High degree of conjugation. Remember UV vis, something highly conjugated, going to be absorbed into visible. See that pi, extended pi conjugation between the rings, the diazo linkage, the other ring, and then the lone pair of the activating group. Question?
So you said earlier that you can use a diazonium reaction to make a phenol.
Yeah.
So I guess you have to, like, how do you prevent in a situation like this there being some, so I don't want to say like polyalkylation, but how do you prevent, like if you were making a phenol, how do you prevent it from reacting with the
Once you get some phenol formed, why does the phenol product not react with the diazonium? Well, that's a good point. Potentially could. Depends on rates. And it may be a problem. It may be that you have to do it a certain way. But yeah, good point. Okay. A diazo dye, or just an azo dye. These azo dyes are everywhere. They also cause cancer. Here's some down here, example of azo dyes. You see the diazo linkage? You'll find this one in Doritos. It's yellow, and they use it to make Doritos even more yellow, so you like them more. Nobody likes faded out Doritos, do you? No. Instead, you like to have this cancer-causing dye in there that makes it look good. Okay? Maybe you like maraschino cherries, and you like to be real red because you just like red cherries. Oh, they put this one in there. It's called FD&C red number 4. You can look on the back and you'll see it as an ingredient. Over here, this one's called Solvent Yellow 124. Let me ask you, which side is the diazonium on, which side is the ring that attacks the diazonium? That is, does this ring attack that nitrogen, or does this ring attack this nitrogen?
The right side.
Yes, the right, we make that bond right there. You make plain diazonium and then this, because that has the activated substitution. That's all just alkyl there. This one is used in Europe to make diesel fuel yellow. Why? Because there's a big cost difference between diesel fuel and regular fuel. And if a company is going to buy a big load of fuel, they want to know that they're indeed getting diesel and not you're trying to sell them the cheaper regular gasoline. So what's a good way to tell the difference? All the diesel fuel is colored yellow, so the person buying it can easily see. Now, of course, somebody could dye the regular fuel yellow, but that's probably more difficult for them to do.
Is yellow 5 one of those same kind of dyes?
Well, they're all that like that. Most all the dyes you see in food are Azo dyes. Popcorn, make yellow. Fake butter, make yellow. You know the factory where they make the fake butter for fake popcorn, and they use the yellow dye. A lot of the factory workers were getting cancer. Okay. So the difference is when you eat your popcorn, you only get a wee little bit, and the FDA has said that it's not enough to cause cancer. But the people that are working in their factory were getting much more exposure. Look it up. Let's see. Prontosil, where do we know that one from? That was actually the first synthetic antibacterial. Way back, some guy, I think his name was Ehrlich, they had this red dye they were used for a variety of things. He decided to put the red dye on bacteria. And it killed them. Well, this was the red dye. And this became, they started using this as a drug. Because way back then, you got an infection and you're likely to die. There's a story in the handout about, I think, FDR's grandchild or something was saved by giving this here. Later on, they found out when this goes into the body, the diazo is cleaved, and that becomes NH2, reductive cleavage. And when that's NH2, what is this? You all halogenated it in the lab a few weeks ago. Sulfanilamide. They realized that this is not actually active. Body cleaves it, sulfanilamide is what's active. Once they figured that out, they stopped giving the dye and they just started giving sulfanilamide. That was probably in the 1930s. And then World War II came along and sulfanilamide was used during World War II. It's actually called a prodrug. A prodrug, the actual structure is not active, but the body converts it to the actual active drug. So that is a good thing there. You can read about the story of Prontosil, etc. Okay, let's look at some another multi-step synthesis. Let's look at the third one here. How can we make this from benzene? Let's see, let's go back. If I take off the chlorine and come back here, can I go forward? Can you take this and coordinate it? No. Why not? Cyano is a meta-directive. have problems. What if I go back and take off
You
the
just said it was a meta.
cyano is a meta director.
Okay, yes.
If I try to chlorinate this, it will not go ortho in good yield. Anytime we do a synthesis, we want to be in good yield. What if I go back and take off the cyano group? Have a chlorine.
You can't do it. You gotta go from
This is an ortho pair director, but how do you put on a cyano group? Can we put that on directly? No, but we just learned how to indirectly put it on. By what type of reaction? Diazonium. So, we got the right director. Let's go forward. What do you want to do first with chlorobenzene? First off, how do you make chlorobenzene? Because we want to start with benzene, chlorine, and what? Maybe FeCl3 or aluminum trichloride, like the Lewis acid. From here, what do you want to do?
Nitrous
If
acid.
you're going to do diazonium, what do you need?
Nitrous acid. You add sodium nitrate, nitrite, and then
Yeah, but you first have to have what?
oh, I think it's making a
You've done this sequence in lab already.
You have to add.
How did you get an iota onto fluorine in lab?
You need an amino group.
Yeah, but before you had, how do you get the amino there?
Nitro.
Nitro. You can't directly add an amino. HNO3 and H2SO4 will give what? Nitro plus what? Ortho plus... Yeah, you're going to have some pair that you're probably going to have to purify out. Jordan.
Do they often like melt at different temperatures? Like, is it easy to like isolate two different ones?
Isomers?
Yeah, like not. Yeah, exactly. Yeah.
You mean distillation? If they're liquids, you can distill them and you might be able to separate them.
Okay.
Or column chromatography. If they're solids, sometimes one will crystallize out selectively. Sometimes it can be tough. Now what you want to do? We got to have the amine, because the amine is what we do the diazonium on. How do you get the amine? 10 and what? HCl? Classical. Filtration might be a little slow. Now that we got that, how do we get home? First we want to do what? Make the diazonium. How do you want to make it? I'll make the diazonium, and then when you get the diazonium, cuprous cyanide. It's two separate reactions. If you don't have the 1 and 2, you're not going to be good. You cannot mix nitrous acid with copper cyanide. Do the nitrous part, then you follow it by the copper cyanide, 1 and then 2. So diazonium chemistry, but diazonium is a multi-step. Comes from the amine. How do you usually get an amine on the ring? The nitro. So it's a multi-step process. Okay, you need to be working others. For example, over here, phenol on the ring. How might you get a phenol on the ring? I don't know. Let's look at the pink handout. This is the purple. I'm going to refer to something on the purple, but we're going to be looking at the pink. Okay, guys, the pink is our last handout, I believe, for the test. We're going to go back to the ring chemistry, not substituent chemistry. Okay. 3 mechanisms. We've covered only one, EAS. We have 2 other mechanisms to cover. Back on the purple sheet, they were roaming in with 2 and 3. Nucleophilic aromatic substitution, NAS. Number 3 will be called Benzyne mechanisms. These 2 mechanisms are going to involve replacing a traditional leaving group. EAS, what do we replace typically? An H. For the other 2 mechanisms, we're going to replace things that we've always called leaving groups, like maybe a bromine, okay, chlorine. It's going to be leaving group chemistry, but it's not SN1, SN2, okay? Same idea of leaving group, but it's not those mechanisms. Because you don't do those mechanisms typically on an sp2 carbon. So we have new substitution mechanisms and we have a traditional leaving group. Okay. Pink sheet. Substitution of leaving groups on aromatic ring. That's warm up. Let me take you through the warm up a little bit here. You take this compound here, orthochloronitrobenzene, we're reacting with sodium ethoxide, an alkoxide nucleophile, we can replace the chlorine. That's an example of replacing a leaving group on a ring. Only one product is formed, there's no isomer. Try to do the same reaction with this substrate, methoxy instead of nitro, there's no reaction. What does that tell you about the importance of the nitro? The nitro apparently made it work. Or the methoxy made it not work, or something. But why does one work and one not? Now if you try this reaction at 300 degrees instead of 25, you will get a reaction. But interestingly, you get isomers. Looks like the nucleophile replaced the chlorine, but how did the nucleophile end up on the next carbon? 2 major products formed here. What you have going on here is 2 different mechanisms operating. There's other things there. Let's go to the next page. You also notice the difference in the heat, 25 versus 300. One mechanism does require pretty high heat. Okay, let's look at this. Substitution by of a leaving group by nucleophile. Very general. Have a leaving group, nucleophile, now leaving group's gone. Very general substitution. First off, the ring is now the electrophile. Where in EAS, the ring is a nucleophile. And the ring attacks electrophiles. We're opposite now. Mechanism for this up here. It's not SN2. You'd never do SN2 in an sp2 carbon. It's not SN1. Because leaving group is not just going to leave and make this cation here, because that's very unstable. Maybe the diazonium, when you make the phenol, that does happen. But typically, avoid that. It's not EAS, because we're reacting with nucleophile. So don't do that. The mechanism is either NAS or benzyne. Let's look at these 2 mechanisms. NAS, also known as that there. So, tell me what you would propose. Obviously, we got to replace this with that. How do you want to do it? What we can't do is what we just said. We cannot just say, okay, this is organic chemistry. Okay? We cannot just do this, can we? because that looks like SN2 and it ain't SN2. So don't do that. So how do we do this instead? Somebody give me a suggestion. You want the chlorine to just leave? I said that's good. What else can we do? A what? Radical? Good, but it's not a radical, it is ionic. Well, let's make sure this bond is drawn in here, okay? First step here is, first off, what type of reactivity do we have here? That's a nucleophile. What is it like to be attracted to? Positive. Which carbon has the most positive? Yeah, I agree it's the one with the chlorine. This attacks here, but instead of the chlorine getting kicked off, we've actually said this before. Whenever you attack something, you break the weaker bond. Which is a weaker bond? Sigma bond to chlorine or pi bond to carbon? Pi bond to carbon. This pi bond moves out onto the carbon. What's here on this carbon then? Yes, lone pair, and that's a minus.
That's crazy.
But we're going to be doing tons when we get to carbonyl chemistry. Pretty basic. Anytime you attack the carbon, you go break the weaker bond. Which is weaker, sigma bond to chlorine or pi bond to carbon? Pi bond to carbon. There you go. That gives us. What do you want to call this step? What did we just do? Give me a addition. Addition of what? Addition of nucleophile. Okay, I'll go with that. Now, is this aromatic? No, that carbon right there is sp3. There's no p orbital. Not aromatic, but it is resonance stabilized. These electrons can come here, these can move out. And we get boom, boom, boom. When we do an EAS, what charge does the ring take on? Intermediate. Positive. Here the ring takes on a negative. Electrons here, electrons out. That there. So our intermediate is resonance stabilized. How many intermediates on the board? No, that's one thing. So one intermediate. That's three different. It's like purple is, how many colors is purple? It's one. It may come from blue, green, and red being mixed together, but it's one color, it's purple. That's just the old resonance thing, right? That's one intermediate, but it's stabilized by being delocalized by resonance. Okay? There's only one more step to get here. You can work with any resonance structure. I'm going to work with this one here. That's my resonator. What do we need to do to get from a product? These electrons then come back in. Now we're going to kick off the better leaving group. Which one's better? O or Cl? Kick that off. What does this give? This arrow movement right there. This is B and this is B. This is your mechanism arrow. Yeah, it reforms the double bond and kicks off the leaving group.
Isn't that essentially what we did on phosphates?
What?
Isn't this essentially what we did when we actually phosphates?
We did an additional elimination? Yeah. Like I said when we started, we've seen this before. It's addition elimination chemistry. Overall, it's substitution. Tell me, is this SN2? No, SN2, you would come in and kick it off directly. Is it SN1? No, you would ionize the leaving group and make carbocaloric. This is a substitution mechanism, but it's neither of those. It's called addition elimination. Because it's on a benzene ring, it's called nucleophilic aromatic substitution because we're reacting with a nucleophile. Addition, elimination. Okay? This is pi bond chemistry, pi bond substitution. All right. Well, I lied to you. This reaction doesn't happen. This reaction doesn't happen. Not with mild heat it doesn't. Doesn't happen. Doesn't happen. I showed you the correct mechanism, but the mechanism doesn't happen here. Tell me why it doesn't happen. Very focused. Why does it not happen? Apparently because what? Not enough activation energy. Apparently, why is there not enough activation energy? Apparently because the rate determining step is too slow. Why would the rate determining step be slow? The intermediate is too high in energy. Let's do a reaction coordinate diagram here. Okay? Very, very quickly. Starting material, product, I'm not going to say here. We got this here. What do you want to call this intermediate? Sometimes it's called sigma complex again, but it's different. But it's an anion. We didn't make a new sigma bond. You could call it the addition product or whatever. Which one's the rate determining step? First one. Yes. The rate determining step here. Okay? If I'm telling you this does not occur, we had to say, well, apparently this is too high energy to be formed at mild heat. How can we make this reaction work? What do we need to do here? Have to lower the energy of this, apparently. It's not happening because that's too high. How do you lower the energy of this? How could we? It's already resonance stabilized, but it's apparently not stable enough. How do we make it more stable? How could we, theoretically? Yes, you need substituents on the ring that will stabilize this even more. What type of substituent? Do we need a donator or withdrawer? How do you stabilize an anion? Withdrawer. Not only do you need a withdrawer, but you need it at certain locations. Would you rather have it ortho, meta, or para to the chlorine? Look where the anion falls. Where does it fall compared to the original chlorine? Ortho, para, ortho. That's where you want your withdrawer if you're going to have this reaction work. For example, I'm going to add here a ketone ortho, a methyl ketone. Add it there, add it there, add it there, add it there. 30 seconds, guys. With such a group added, it will now work. Because right here, we have another resonance structure. Since this group is there. Draw the other resonance structure, we'll look at it next time. That's the requirement. We'll review this first thing next time.